welcome to lesson 6. It can be found in your textbook in section 8.2. However, today we're going to look at part 2 of what we learned from yesterday. So we're still looking at the equilibrium of weak acids and bases, and a key term that you want to know is this one right here, the percent dissociation. The percent dissociation of a weak acid is the fraction of acid molecules that dissociate compared with the initial concentration of the acid. It depends on the Ka for the weak acid and the initial concentration of the weak acid. So I'm just going to reword that to make a little bit more sense for you. So basically, the percent of dissociation, I'm going to just write that, and then is equal to okay, what that says, if you can't see it, is basically in order to find the percent dissociation, you need to take the dissociated molecules divided by the initial concentration of the acid. So basically, all you're going to do to find it is you're going to put the concentration of your hydronium ions divided by your initial concentration of the acid. You'll see when we do an example together, though, it'll make more sense. Another thing that we're going to look at today is polyprotic acids, and I talked a little bit about this yesterday. So remember, polyprotic acids have more than one hydrogen atom that actually dissociates. Each dissociation has its own Ka value. Okay, the Ka values for any reaction can actually be found in the back of your textbook in Appendix E. So you will be using that for many of your homework questions. However, when it does come to a test or a quiz, you'll be given the Ka value, so you won't have to look them up. All polyprotic acids, except for sulfuric acid, which we already know is a strong acid, are considered to be weak acids. Their second dissociation, right, so they donate one hydrogen and then they have the ability to donate another. So on their second donation, it is much weaker than their first. We should only consider their first dissociation when calculating the concentration of the hydronium ions and the pH. So if a question asks you for the pH and it is a polyprotic acid, you only have to take the pH of their first dissociation, because the second one will be so small in terms of the percent or the amount of hydronium ions, so it will not actually have an effect on the pH. So like I said before, in order to find any of your Ka values, you can refer to table E10 in the back of your textbook, which is found in Appendix E. And that will give you the ionization constants for polyprotic acids. So you're looking for your Ka values in the back of your book. There wasn't a lot of questions where this was applicable, but it will be applicable in this chapter. If your initial concentration of your acid, you take that and you divide it by your K value, if that is greater than 500, then the change in the initial concentration X is negligible, meaning that it is so small, the change that's actually occurring, that it's not having an effect between the initial concentration and the concentration at equilibrium. And it can therefore be ignored. And we're going to do an example where that is actually going to happen, so it'll make more sense. However, if you do put those values in and you get it less than 500, the change in the initial concentrations is not negligible, and the equilibrium equation will actually be more complex and require you to do a quadratic equation. But like I said, in this unit, most of the time it is going to be greater than 500. You do need to show that in your work that you are checking to see it's greater than 500 in order to get full marks. Okay, so let's do a question together. So we'll start off with the first one here. This is on page 400. It's question number 19. Calculate the pH of a sample of vinegar that contains 0.83 moles per liter of acetic acid. What is the percent dissociation of the vinegar? So in order to start this out, we do need to create our ice tables that we were practicing from the previous unit. So let's write out the equation first. So this is what I was talking about yesterday. So you have a equation like this, you don't know how to set it up properly. So it's talking about vinegar. Vinegar is the same as acetic acid. So acetic acid is CH3COOH. You're going to add that, with any acid you're going to add water. And your products are, remember that the acid is the proton donor and the base is the proton acceptor. Well, vinegar is an acid, so it's obviously going to lose a hydrogen and donate it to the water. So our products are going to be H3O plus and CH3COO minus. So they've donated a hydrogen, so now we have that negative charge because we've lost a proton or positive charge. So again, we're going to create that ice table that we learned from before. So ICE. Remember what those represent though. I represents the initial concentration. C represents the amount that needs to change in order for it to reach equilibrium. And then E would obviously represent equilibrium. So the initial concentration of acetic acid was given. So remember, that's the same as vinegar. 0.83. Water, looking back to our very first lesson for chapter 8, remember that water can be ignored. So we can actually put in nothing for water. Just leave it as if it's not even there. And remember that our products will always start at 0 because they haven't been formed yet. So this is 0 and this is 0. In terms of the change, we know that our reactants are going to go down, so we're going to have a negative X. Remember though, if we did have moles in front of any one of those, we'd have to put negative 2x or negative 3x depending on what moles were in front. But in this case, we have 1-to-1 ratio all the way through. So our products, they're starting at 0, so the only thing they can do is go up. So this would be plus x, and this would be plus x. Therefore, at equilibrium, we're going to have 0.83 minus the x. We're going to have x and x. So that would be your ice table right there. At this point, you can go in the back of your textbook to your Appendix E, and you can look up the Ka value for acetic acid. So if you do that, you'll find that the Ka value for acetic acid is 1.8 times 10 to the negative 5. So remember, I told you that you always have to check in order to get full marks if it is greater than 500. So that's how, I'll show you how we set that up right now. So we want to check HA divided by Ka. We want to check to see if that's greater than 500. So HA represents our initial concentration of our acid. So in this case, it's going to be 0.83 divided by our Ka that we looked up in the back of our textbook, which would be 1.8 times 10 to the negative 5. If you do put that in your calculator and ends up being greater than 500, So what that means is we can ignore the change in our initial concentration of our acid. And the reason we can do that is because the change, whatever x is going to end up being, is so small that the difference between here and here is going to be exactly the same. It's going to be so small, the change, that it has no effect on the equilibrium. So because we found out this is greater than 500, we can actually cancel this x out, and we don't need to use it when we plug it into our products over reactants equation. We can't cross out these x's though, because we need to find those values. It started at 0. We want to know what that change was in order to get to the equilibrium for H3O plus and CH3COO minus. Okay, so when it's greater than 500, you can only cross off the x that is part of the initial acid. Okay, so now we're going to plug it into our Ka equation. So Ka, so we're going to do products over reactants. So we're going to do CH3COO So that would be our Ka equation. So now we can substitute our values from our ice table into there. And we can also substitute in our Ka value. Actually, I'm going to erase this. I'm going to put in my Ka value. So our Ka, we said, was 1.8 times 10 to the negative 5. If we substitute in our values at equilibrium, right, which is right here, we know that our products are both x, so I'm just going to put x squared because it'd be x times x. And then on the bottom, I'm going to take away that negative x, so I'm going to be just left with 0.83. Okay, then it's just a matter of solving for your x. So I'm going to take the 0.83 and bring it to the other side. So I'm going to be left with 0.83 times 1.8 times 10 to the negative 5. If you put that in your calculator, you end up with 1.494 times 10 to the negative 5. Now, in order to get x by itself, we're going to have to take the square root of both sides. We're going to take the square root here and the square root here, and you end up with x is equal to, remember when you take the square root of something, it's plus or minus. So plus or minus 3.87 times 10 to the negative 3. So we're not actually done the question because it's asking us for the pH, and at this point we finally figured out what the concentration of our H3O plus is. Before we could even find pH, right? Remember our equations from the previous day? In order to find pH, we need to have negative log of the concentration of H3O plus. By finding our X, we have also found our H3O plus because X is equal to, at our equilibrium, H3O plus. So we can write here the concentration of H3O plus is equal to, obviously we can't use the negative value, and in order to understand that, right, H3O plus started at 0, so you can't take away something that you don't have. So obviously it's the positive value. So H3O plus is equal to 3.87 times 10 to the negative 3. So by having that now, we can actually find our pH. So let's do it right beside it. So pH, remember, is equal to the negative log of H3O plus. So let's substitute our values in. So we substitute our H3O plus concentration that we found from before. And if you do put that into your calculator, you end up with a pH of 2.41. So we've calculated the pH, but it also asked us to find the percent dissociation. Okay, so we still have to use that equation that I showed you on the note that we were doing previously. So I'll refresh what that is. The percent dissociation is equal to the concentration of our hydronium ions divided by the concentration of our HA, or in this case, our acetic acid. So it's basically the percent dissociation is what it's asking you is how much of it actually dissociated into its ions. So remember, with a strong acid, you're going to get 99% dissociation. And with a weak acid, remember that I said before, the amount that's going to dissociate in a weak acid is usually less than 1%. So this will let us know whether it is a weak acid or a strong acid. So if we substitute our values in, our H3O plus is 3.87 times 10 to the negative 3. We're going to divide that by 0.83. If you put that in your calculator, sorry, we're also going to times by 100 so we can get a percentage. You put that in your calculator and you end up with a value of 0.46%, which is less than 1%, which tells us that this is a weak acid. If this value was over 95 or 99%, then you know it's a strong acid. But weak acids will always dissociate less than 1% of the time. So out of everything that's in the water, only 0.46% of it is actually breaking up. This reaction above here, this is only happening and breaking up into hydronium ions and CH3COO minus 0.46% of the time. Most of the time you'll have this just floating around in water without it being broken up. That's what that means. Okay? If you do have any questions with any of these, just make sure you could just write down the time on the video of where you were having any questions, and then feel free to ask me the next day so we can go through it. Or if you even want to go through any one of these lessons as a team with me and you, just let me know the next day, and by all means I can sit down with you and go through it with you. Okay, we're going to move on to polyprotic acid. So we're going to move on to the next question. Okay, so this question can be found on page 403. It's question number 27. You might run out of room on this question, so I don't know if you want to do it on a separate piece of paper because it does take up a lot of space. Hydrosulfuric acid, H2S, is a weak acid that is sometimes used in analytical work. It is used to precipitate metal sulfides, which tend to be very insoluble. Calculate the pH and the concentration of the hydrogen, or HS minus, so it's given away a hydrogen, of a 7.5 times 10 to the negative 3 moles per liter solution. So the first thing we need to do is write out an equation of what's happening. So we have H2S. Remember, we're going to add water to that acid. Acids always donate their protons, so we're going to be left with the same acid minus a hydrogen, and that hydrogen is going to be picked up by the base, which in this case is water. So we're going to now have that hydronium ion, H3O+. Then we need to substitute what is given. So we know that the initial concentration of hydrosulfuric acid is 7.5 times 10 to the negative 3 moles per liter. That is given in the question, so we're going to plug that in. Sorry, we'll put our I, C, and our E. So 7.5 times 10 to the negative 3. Remember, water we don't need to count for. Our products always start at 0. The change in our reactant is going to be negative X. Our products can only go up, so we have positive X, positive X. So at equilibrium, we're going to have 7.5 times 10 to the negative 3 minus X. And here we're going to have X and X. Again, we have to look up the Ka value in the back of the book for H2S. So if you look on page 597, you will see that the Ka value is 8.9 times 10 to the negative 8. Okay, so we need that Ka value in order to figure out if we need to ignore X or not. So whether it's greater than 500. So if you plug that in, so remember it's just HA divided by your Ka must be greater than 500. So if we plug in 7.5 times 10 to the negative 3 and divide it by our Ka, which is 8.9 times 10 to the negative 8, you will actually see that it is greater than 500. So it is greater than 500, so that means that we can ignore X. So in this case, X is negligible. It's going to be so small that it's not going to make a huge difference. We're then going to plug it into our products minus reactants equation. So our products, 8.9. So that's our Ka values. Remember, Ka is products over reactants. Our products at equilibrium are both X, so I can put X squared, divided by our reactants, which is just H2S, which we found in equilibrium to be 7.5 times 10 to the negative 3. Remember, we're not keeping that X because it is greater than 500 when we substitute it into that equation. So now it's just a matter of rearranging it. So if you substitute everything in, rearrange it, you end up with X squared is equal to plus or minus 2.58 times 10 to the negative 5. So obviously, again, we're not going to take the negative value because we started out with 0. There's no way that we could take away from something that we don't have. So we're looking at the positive value. So this would be your first dissociation. And now we're going to do a second dissociation with the information that we found. So here we're left with HS negative. So we're going to start with that here because it can donate another proton. So again, we're going to add water to that. Water is going to pick up that hydrogen and again form another hydronium ion. And now what we're going to be left with is just S. And now it's going to be to the negative 2 because it's lost 2 protons which carry positive charges. So it doesn't have that positive charge anymore, so it's S to the negative 2. Every time you lose a proton, which is hydrogen, you get a negative charge. So now, if we look above, sorry, this should not be X squared, that was my fault. We got rid of that when we took the square root. So now we see that plus or minus 2.85 times 10 to the negative 5, that is the value for HS negative. So we can substitute that in down here. So 2.58 times 10 to the negative 5. Water we don't count for. And our products again are starting at 0. Our change is going to be negative X for our reactants, positive X for our products, and therefore at equilibrium 2.5 times 10 to the negative 5 minus X, and then just X and X. Again, you want to do and make sure that it is greater than 500, and maybe you don't have to do a quadratic formula. So you're going to do HA, which is just your HS negative, right? HA just stands for your initial concentration of your acid. Divided by our Ka must be greater than 500. If you put that in your calculator, you see that it is actually greater than 500. Therefore, we do not have to use this X. It is so small that it would not make a difference. So again, we need to plug it into our products over reactants. So our Ka in this situation we didn't look up yet. So if you look in the back of your textbook, you'll see that the Ka value for HS negative is 1.0 times 10 to the negative 19. So now we can substitute that into our equation products over reactants. So 1.0 times 10 to the negative 19 is equal to, so that's our Ka. Our products over reactants, our products at equilibrium are both X, so we can put X squared, divided by our reactants. Because we got rid of the X, we're just going to put 2.5 times 10 to the negative 5. If you rearrange that and then take the square root of the X, you end up with the value of plus or minus 1.61 times 10 to the negative 12. Obviously, again, we're not looking at the negative value. It'd be a positive value. So in order to answer the original question, it asked you for the pH, and it asked us for the concentration of HS negative. Well, we already found the initial concentration of HS negative is 2.58 times 10 to the negative S. So let's just summarize here at the bottom. So the concentration of HS negative is equal to 2.58 times 10 to the negative 5. And now, if you refer back, I'm going to show you guys this for a second. Go back to our original note, and there was something I pointed out to you that I wanted you to take note of. Here it said, consider only their first association when calculating pH, which is exactly what the next step we need to do in that equation is. So if we go back here, in order to calculate our pH, we're going to look at what the value was from our original dissociation. And in our original dissociation, we found our X to be 2.58 times 10 to the negative 5. You'll see at the second dissociation, our value ends up being 1.61 times 10 to the negative 12, which is so small that it has basically no effect. So we only take the pH of the first one. So remember, to find pH, we're going to take negative log of the concentration of our H3O plus. So again, right, this X represents not only the concentration of our HS minus, but it also represents the concentration of our H3O plus, our hydronium ions. So we're using that value in here to calculate our pH. If you do put it in your calculator, you take the negative log of 2.58 times 10 to the negative 5, you end up with a pH value of 4.59. I'm just going to recap this. If this makes sense to you and you're good, you can stop the video here, but I'm just going to do a quick recap of what we did for this question because it is a little confusing. Okay, so first of all, the goal of this whole question is to find the pH and the concentration of HS minus. It is a polyproduct acid, so it does have to go through two dissociations. The first dissociation is we're going to take H2S, which is hydrosulfuric acid. We're going to add water. The acid is a proton donor, so it's going to donate its hydrogen to the water to give you a hydronium ion, and we're going to be left with HS minus. The Ka values will never be, well, sometimes be given, but in this case they're not given. You just look up in the back of your textbook on page 597. We need to set up an ice table in order to solve for HS minus. So we set it up the same way we've always set up ice tables. You need to check that it's greater than 500 to cancel out the X. And I'm just going to rewrite this in case you forgot that Ka is equal to products over reactants. So that's where these numbers in red are coming from. The Ka for this equation is 8.9 times 10 to the negative 8. Our products, we use the values we got from E in our ice table. So they're both X. We're going to put X squared. Divided by our reactants, which is just 7.5 times 10 to the negative 3. You substitute everything and rearrange it. You end up with X is equal to plus or minus 2. That's a point there, in case you didn't notice that. 2.58 times 10 to the negative 5. That X, right, if we substitute that back into our equilibrium values, represents the concentration of HS minus as well as the concentration of H3O plus. It also is a really small number, and that's proved to us that we didn't have to include this X because it's basically taking 7.5 times 10 to the negative 3 and taking away 0 because it's such a small number. After we've done that, we need to do a second dissociation because it's a polyproduct acid. That HS minus can then be broken down further to give us S minus 2 plus the hydronium ion. We know what the concentration of HS minus is from the previous dissociation, so we can carry that number through and put it in here. Our products always start at 0, so that's why we put the zeros in. Reactants go up, products go down. Reactants go down, products go up. Again, we're going to put in to see if it's greater than 500 to see if we need to keep the X, and it is greater than 500 if we substitute those values in. So we don't keep the X. Again, we're still doing that equation from above here. Ka equals products over reactants. So we substitute our values in. Our products are both X at equilibrium. So we're going to put X squared on top, divided by our value of HS minus, which is 2.5 times 10 to the negative 5, and make that equal to our Ka, which we looked up in the back of our textbook. Rearrange it all, substitute, solve for X. You get plus 1.61 times 10 to the negative 12. Once you've gone through the two dissociations, you're then going to finally answer the question. We already found the concentration of HS minus from the previous dissociation to be 2.58 times 10 to the negative 5. The pH, you only want to take the pH of not both of the H3O pluses, but only the H3O plus from the first dissociation. So we only care about H3O plus here. Whatever that value was, we found to be 2.58 times 10 to the negative 5. You substitute it into the equation we learned in the previous days. So pH is equal to the negative log of H3O plus. We substitute our values in, and we get a pH of 4.59. Okay, so hopefully that makes a little bit more sense to you. Definitely make sure you do the practice questions in this section because it can be complicated.